saying. Oh, are we? Bert? Is that a yes?
Yes.
Oh, you're right. People are coming in. Excellent. So welcome, everyone. Please introduce yourself in the chat as you come in. Just let us know your name and where you come from. By the way, we have more than 200 participants registered for this meeting. So it's going to be fun. No, we keep saying that and I keep forgetting. What kind of music do you think we should actually be playing while we're waiting?
Supermassive black hole, black holes and revelations. Oh, so I'm sorry. I don't have a music list.
Royalty-free music. This is going on YouTube, and they will copyright it and take the video down if we play music that is owned by somebody else.
Yeah, but we can actually play it at the beginning and remove that part. We were doing a little bit of editing because there's lots of discussions here. So we have people from New Zealand already coming in. Midnight Coffee and Webinar, awesome, welcome. Florida, Ohio. Let's see, we do have people from Canada, Illinois, New Jersey, India. Hi, India. Good to see you guys again. Belgium's here, Brazil is here. It's very nice. Welcome, welcome. Hey, hi, Sebastian. UK, Brazil, US, Missouri, very nice. Montreal, cool. It's so nice to see where people come from. So we are an international community, and if not anything else, this demonstrates it. Yes, I would love to come back to Brussels. Brussels is one of my favorite cities in the world. So good to see you here. Hi, Sri Lanka, Arizona, Canada, Argentina, California. Hi, Maureen. Very nice, very nice. Hi, Taiwan. Oh my goodness. I know that Taiwan is like 12 hours away from us. So we're talking about midnight there. Oh, 2 o'clock in the morning. Hi, South Africa, Nebraska, Mexico City. How wonderful. The UK. Not sure what DMV is. Hi, Jay. Hi, London. What I want to see all panelists and attendees.
Oops. Yeah, and then I didn't do it.
It's already set to all panelists and attendees, I think.
Yeah,
Hi, Philippines. Oh, how wonderful.
You have to physically do it yourself. You can send it to either.
Yeah, we should actually give that instruction at some point. Very good. New Mexico, how nice. Cool. So we have a couple more minutes to get started. So one thing I want to do, the first thing I want to do, hi, Franz, is actually pop up a short poll. So while we are waiting to start, if you don't mind filling this poll and let us know if you have a favorite object. Hi, India. Hello, Quebec. Wonderful. Ah, Slu is here. Good to see you. Very nice seeing you. All right. And we have people actually telling us their favorite subject. Hola to Catalonia. Hi, Mercedes. Right, shall we wait a couple of more minutes so people come and settle and fill in the poll? But we are at 89 participants. The number increases with time. We're having an Astro party. 90, 91, yeah. It's really cool. It's really cool.
Great to see such a crowd.
Yeah, from all over the world, huh? Hi, Florence. Good to see you. Yay. So as you come, a reminder, please fill the poll. Just give us an idea of what kind of topics you like when it comes to the high energy network. And we're going to start in a couple of minutes. Yes.
So for those of you who are new to Zoom, there is a Q&A button that's probably in the lower right part of your screen.
And this is going to be part of the introduction.
Oh, I'm so sorry, Stella. I jumped the gun.
Yes, you did, but that's okay. So we are at 100 participants. So I'm going to close the poll here. So with 32%, no, with 43%, gravitational waves win, but there we have good responses for other subjects as well. And I hope by the end of this presentation, you'll learn more about other high energy objects to actually not be able to choose your favorite. So how about that? So let's get started. My name is Stella Kafka. I'm the Executive Director of the AAVSO, and it's a great pleasure to actually bring you and introduce another webinar here at the AAVSO. Today, I am joined by Bert Pablo, Arto Ksanen, Greg Sivakov, and Zabludov, and we're going to be talking about the high energy network, high energy objects. Before we get started, a couple of logistics. Just showing you, there are two buttons at the very bottom of your screen. One is for chat and the other one is for Q&A. We're going to be addressing questions at the very end of the seminar, but if you have any questions for our panelists, for our presenters, please use this particular button. Also, if you have any sound problems, there's a button here that says mute. It has a little microphone, and if you click there, then you can see your sound settings. We cannot fix your audio settings from headquarters, so please be aware that this button is going to help you work with whatever issues you might have. Also, I would like to acknowledge the Boyce Research Initiative that actually very generously helped us bring this workshop to you. The Boyce Research Initiative and Education Foundation, Boyce Astro, provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals like the Journal of the AVSO. They have been a partner and close ally to the AVSO for years, and they are supporting this webinar. We're really very grateful for that. So with that, without further ado, I am sitting here for Dave Hinsel, who is our observing section leader, and I would like to give you a very short introduction of what the AVSO International High Energy Network is. And I'd like to start with a little bit of history. It was established in 2000 after the first high energy workshop for amateur astronomers that took place in April 2000. This started a GRB network, gamma ray burster network, and it was actually a great success, detecting many GRBs, afterglows, and discovering a few of our own. And actually, the expansion of the AVSO International Gamma Ray Burst Network was actually the High Energy Network, which since 2005 has continued to pursue gamma ray bursts, blazars, polars, and other kinds of high energy astrophysical phenomena, mostly in collaboration with professional researchers requesting our help and also independent researchers. So pretty much this network has been distributing notices from high energy telescopes such as Swift, Integral, and Fermi, and requesting follow-up observations from ground-based resources here at the AVSO. The network has been dormant for a while until pretty much last year when Dave Hinsel undertook the task of leading the effort to resume the relevant activities. The follow-up of GRB optical afterglows continues to be a major focus of the network today, but also all objects with strong X-ray and gamma ray signature and optical counterparts are included. So these are active galactic nuclei, blazars, BLX systems, magnetars, pulsars, flare stars, X-ray binaries, all kinds of objects, including gravitational wave emitters. Here's an example of work that the AVSO High Energy Network has been doing. This is a blazar. This is BLAC, which is actually a very energetic type of black hole powered galactic core. A black hole is a contraction of mass so dense that not even light can escape its gravitational pull. In this particular case, we're talking about supermassive black holes. We're talking about more than 200 million times the mass of the sun, in the case of BLAC specifically, that are in the very center of a galaxy. In these galaxies, the cores propel big jets of electrically charged particles that are actually being propelled outward, presumably in the speed of light, at the speed of light, and supported by very strong magnetic fields. This is actually an artist's conception of how one of those black holes look like, BLAC in particular in this particular case, that actually became part of a Nature manuscript in 2008 and was discussing the X-ray and the optical emission of this particular black hole. And here you can see the AVSO light curve. All these kind of lines and wiggles that you see are real, and they have to do with instabilities either in the jet or the black hole itself. Recently, we have been working on a second outburst of a blazar. This is a blazar that has been observed since 2005. So it had an outburst already, and the second one was actually discovered by Adolfo Dariva, one of our observers from Spain, and was observed immediately by other AVSO members. So this is pretty much an ongoing program, an ongoing project that members and observers of this particular section are undergoing right now. So what are we planning to do? What are we doing now? Well, we're following exploring the dynamic universe. We're following all kinds of objects, targets from multispectral and multi-messenger astronomy. We have long-term campaigns on objects of interest and something about gravitational waves. And it's just a preview of what we're going to hear more today. So if you want to learn more about this section, please go to the webpage. You can find all kinds of resources about objects in the high energy network. You'll find a way of joining the mailing list and the forum to discuss different projects. And of course, you're going to find targets and information about high energy network. So in this, right now, I'm going to stop talking, and I would like to introduce our first speaker, Greg Cvqni, who is going to talk about something spooky. Go, Greg.
So good morning, evening, afternoon, wherever you are, everyone. My name is Gregory Cvqni, and today I'm going to be talking about hunting the stellar undead. So talking about the vampires, werewolves, zombies, banshees, and dancing skeletons in our universe. Before I begin, I'd like to recognize that I'm coming to you from the University of Alberta and from the city of Edmonton. And this location is basically located on the original Treaty 6 territory. And I want to recognize the history, language, and cultures of many First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. In particular, Cvqni Waskahikan, which is the original traditional name of Edmonton, which means Beaver Hills House, was a traditional meeting ground for many indigenous communities, including the Cree, Saulteaux, Nakota Sioux, Blackfoot, and the Métis peoples. So with that, I'd like to give us a basic introduction to the stellar undead and how we do a little bit of that hunting, both as professionals and with the citizen community like AVSO. So many of us are used to thinking about the undead from popular culture, whether it's vampires like Nosferatu or Dracula, werewolves, or zombies. Of course, there's the fast and the slow types of zombies. These things now make up actually a major part of our pop culture. And it turns out that I like to use the undead as ways of remembering some of the behaviors of high energy objects. But there are more than just these sort of traditional ones in big in our pop culture. There are also things like banshees, which originally come from Ireland. If you haven't heard of banshees, they're known for predicting death through their wails of cries. They're also known in some role-playing games of their cries being so loud that they actually cause people to expire. And of course, we also have skeletons. And as we'll talk about, we're not just gonna have skeletons, we're gonna have dancing skeletons in this talk. So sometimes the undead can be funny like this, sometimes they can be scary, but in all cases, I'm gonna talk about the stellar undead, which I think are exceptionally interesting. So we mentioned the high energy network. And so what does that mean? Well, when we're talking about high energy, we're talking about the electromagnetic spectrum. And basically, all of the electromagnetic spectrum has different properties of wavelengths, frequencies, or energies that are all related to one another. The shortest wavelengths, highest frequency, highest energy component of the electromagnetic spectrum are gamma rays and X-rays. If you go a little bit to lower energies, you get ultraviolet, and then you get to the optical light that we're used to thinking about. Now, when we talk about high energy, most people think about X-rays and gamma rays, although I think you probably should include ultraviolet as well in thinking about what is a high energy astrophysically speaking. But there's surprisingly a big connection between the highest energies and the lowest energies. So radio, where you start having wavelengths as big as people or bigger even, It turns out that oftentimes high energy objects are not just bright in the X-rays, bright in the gamma rays, bright in ultraviolets, they're bright in the radio. So it turns out that, of course, these objects are across the electromagnetic spectrum, but traditionally high energy objects have been most studied at the high electromagnetic spectrum and the low energy electromagnetic spectrum part. But that's not to say that the optical window, which is what most of us have access to from the ground, isn't important. And as we'll see, they play a key role. One of the things to note, though, about the electromagnetic spectrum is our atmosphere plays a key role also in limiting what we can observe from the ground. So essentially, only optical and radio frequencies are really easy to observe from the ground. Everything else requires extra effort, either getting very high or getting even into space in order to do observations. Now, one of the things that I think unites most aspects of the high energy network objects is that the ways in which they're generating energy tends to come from the most efficient way of generating energy. So most of us, we're used to thinking about generating energy from gasoline. So if you imagine for this explanation, I'm going to imagine a kilogram of material. And so if I take a kilogram of gasoline and I put it into a Toyota Prius, a very energy efficient car, you can go 12 miles. For comparisons, if you think about explosions, the nuclear bomb in Hiroshima, that's about 50 millionth of the Hiroshima bomb's energy output. Now, the other type of energy we're used to dealing with our own lives, and maybe not directly dealing, but at least benefiting from, are nuclear reactions. And for the most efficient nuclear reactions, the fusion reactions, if you take a kilogram of material and let it undergo fusion, you can go all the way to the moon in that Toyota Prius. Granted, you'll have to escape the Earth, but that's another question. And that's about the energy in one explosion from a Hiroshima bomb. But if you take a kilogram of material and you let it fall onto a stellar mass black hole, because the black hole is so tiny and you can get so close to the black hole, you can actually get the most energy efficient transformation in the universe, and that travels 70 times farther than the moon in our Toyota Prius. And that would be, of course, equivalent of 70 Hiroshima bombs. So oftentimes we're going to be talking about very compact objects because letting things fall onto black holes are one of the ways in which you can extract a lot of energy. The other thing we have to think about is, why am I talking about the stellar undead and not just compact stars? Well, it's because if we think about the lives and deaths of stars, all stars eventually die. The most massive stars live fast and die young, and when they run out of the fuel that generates the typical light that we see from them, nothing will be able to support their collapse. They'll fall all the way down to an infinitesimal point, forming a black hole. For the least massive stars, what happens is a much slower dance. So while high mass stars can live millions of years, low mass stars can live billions of years. But at the end of those billions of years, eventually we run out of fuel and the object starts collapsing. But as electrons get very close to each other, a quantum mechanical effect which allows only two electrons to occupy the same space, one spinning one way and one spinning the other way, this quantum principle means that you actually can generate some pressure support and you can stop that gravitational collapse. And you'll form a white dwarf where you're supported by electron degeneracy pressure. And a white dwarf is about the mass of the sun, but the size of Earth. Now, on the other hand, if we're slightly in between the two, it turns out that the collapse creates something that is so massive that the electron degeneracy pressure can't stop it. So instead, it starts to collapse more. Protons and electrons will combine to form neutrons, and then neutrons can act like electrons in the fact that they can only combine the same space, one spin this way, one spin this way, and you can support yourself with neutron star degeneracy pressure. Support yourself with neutron degeneracy pressure, forming what's called a neutron star. And that neutron star is about the mass of the sun, but the size of a typical city. So these are very compact objects. The white dwarf, the neutron star, and the black hole most of all. Now, it turns out that the black hole has something called an event horizon. That event horizon is about 3 kilometers for a solar mass black hole and increases as the mass of the black hole gets bigger. So they're slightly smaller than neutron stars, but we can't actually extract all the energy of going down to the infinitesimal point. So what happens, your star lives its life, then it undergoes its death, and we're left with a white dwarf, a black hole, or a neutron star, the so-called stellar dead. But I'm going to be talking about the stellar undead. So the first type of stellar undead I want to talk about are stellar vampires. So what I show here is a picture of a black hole X-ray binary. We have a component star. That component star, that donor star, is having material flow out from it because it is very close to the black hole, or a neutron star for a neutron star binary. It falls onto a disk of material that goes around the black hole. That disk of material can eventually get so hot that it ionizes and collapses rapidly onto the black hole or neutron star, leading to an outburst of bright emission, and we can sometimes see relativistic jets beaming away from these objects. And sometimes these objects are actually very highly variable. So this animation here is about a real-time animation, and in X-rays, we can occasionally see evidence of material that is rapidly likely going around the black hole, and sometimes that material can even lead to ejections of material that will detect in jets, largely in the radio. And because these objects are eating another star, I like to think of them as stellar vampires. And it turns out that AVSO members do observe these stellar vampires. We often make alerts when one of these feeding frenzies occur. So what's shown here is a plot where on the y-axis, we have magnitude, or how bright the object is. On the x-axis, we have time in days since December 15th, 23 at noon. And this particular outburst was bright for about 12 days. But during that outburst, we see a variety of activity. The blue dots represent X-ray emission, which you can only get with satellites. But the other colored dots represent ground-based optical observations, many of which were done by AVSO members. And you can see that these things are varying quite a bit. And for those of you who are not used to the magnitude system, there are 2 things to remember. The magnitude system is bass-ackwards. What I mean by that is that the brighter you are, the smaller the number is. The other weird thing, it's a weird logarithmic type of system. So every change of 5 magnitudes is a change of 100 in how bright something is. And in fact, you can see this thing is varying on very small time scales. And I love this from a Nature paper in 2016. 4 AVSO members were actually co-authors on that Nature paper. I love this quote from Bill Goff, an AVSO observer and member. "It is not a star I normally observe, but when I saw AVSO Alert Nurse 520 requesting observations, I decided to get on it. The observations made on this target were immediately exciting. Seeing changes greater than 1 magnitude in less than an hour, and some high-frequency changes occurring in the minutes range, was a wonder to see. I kept imagining how this target must be going through unbelievable eruptive changes." So these are one of the stellar undeads that we can hunt together. Excuse me. Now the other type of objects, the next type of object I want to talk about are these neutron stars. And I like to think about neutron stars as zombies because just like zombies, you really can't keep them down. So in particular, neutron stars are known for behavior. They're also known by another type of name called pulsars, where they have radio emission and they're spinning, and if you happen to be in the line of sight of that radio emission, you see a pulse of that emission on a very periodic case. So we have these stellar zombies. After their death, they're still alive, so to speak. But it turns out that neutron stars can also be at the in an X-ray binary, and so you've got a zombie that's also a stellar vampire. And in fact, sometimes these stellar vampires undergo changing behaviors, where sometimes they're more like zombie, the pulsating or the accreting black hole X-ray binaries, and sometimes they're more like the pulsars. Now, the next type of object I want to talk to you about are the stellar werewolves. Now, when I talk about a werewolf, the thing that we most think about is that every full moon, a human turns into a wolf, and that's what makes a werewolf. Some objects in astronomy are strictly periodic. Perhaps you can think about the pulsars as not just zombies, but zombie werewolves. Unfortunately, it's not every month that they're turning into a werewolf, so to speak. It's every second or sometimes even milliseconds. But realistically, their behavior is the same all the time, and so maybe you don't call that a werewolf, it's just that we happen to see them because they're post-emission. But objects like the cataclysmic variable, where we have a white dwarf instead of a black hole or neutron star eating from a nearby star, will undergo an outburst. And so this is really a change in behavior. So this really is a werewolf-like behavior. And this behavior occurs not quite periodic, but fairly close to periodic. So this is one of the most complete light curves that the AAVSO has. This object, SS Sig, was observed before the turn of the 20th century, as in our records, and it goes up, and although I cut the data off here in 2010, we continue to get data on this object basically every day. And there is just tons of information we get from this particular object, but it turns out that these outbursts, these werewolf behaviors, you also see in the neutron stars and the black hole X-ray binaries. They're just not as quick, and not in all of them. We have a few sources which seem to turn into a stellar vampire werewolf zombie, or sorry, stellar vampire werewolf every year or so. So both some of the dwarf nova and the X-ray binaries are these stellar vampire werewolves. And the neutron star ones I call stellar vampire zombie werewolves. It's starting to get complicated, folks. Now, it turns out that there's when the most massive stars die, the black holes and the neutron stars, the death of that supernova, the death of that object, a collapse, is so violent that they often lead to a bright pulse of emission called a supernova. And these supernovae are so bright that you can clearly see the supernova appear, and it's as bright as an entire galaxy. Now, I like to think of supernova as sort of the death screams of a star. And for supernova in particular, we get the scream, this immediate pulse, this immediate emission, and then we see the remnant. So this is an X-ray picture of the remnant of the Cvqni supernova. And there happens to be a neutron star, a zombie, stellar zombie, at the center of this death scream echo. But it turns out that some of the death screams are not just normal death screams, they're extreme death screams. So when a very massive star collapses, one of the things that can happen is it can actually form a jet within itself. And it forms this jet that can be seen in the supernova explosion. And if that jet happens to be pointing right at you, what you see is you see a very big pulse of gamma ray emission, a long gamma ray burst. Long in this question says that the gamma ray and X-ray emission that comes from this burst is more than 2 seconds in duration. We also get two objects that are orbiting around each other, dancing around each other, that start spiraling in together, and eventually they collide. And we think this also can make a powerful black hole or a neutron star and make this jet of material. These tend to make shorter gamma ray bursts, so we call them short gamma ray bursts. And because in some ways, the long gamma ray burst is just sort of an extreme death scream, I like to think about this, these two objects that are announcing that they're about to die are these Banshees. And it turns out that, yes, there's gamma ray and X-ray emission, but as the jet of material expands out, it also interacts with the interstellar medium around the star and the material that the star put out when it was dying and in its late stages of life. And this collision creates lots of shock waves, which leads to something called a afterglow, which Ardo is going to be talking about. And so I won't talk about AAVSO follow-up of those. Now, I mentioned the idea that we've got two objects dancing around one another. And this is a simulation. If these objects are black holes, the green emission that you're seeing come off here is not really emission. It is a bend in the fabric of space-time. It's complicated, but it turns out that this bend in space-time creates what's called a gravitational wave. Now, as the objects get closer and closer together, the gravitational waves get stronger and faster. And eventually they collapse, and then, of course, the gravitational wave ends. Now, it turns out that when we do this, and I'm not sure if you're going to be able to hear the sound, so let me just make sure my sharing that I have the sound turned on. Whoops. I will fix that 1 second all. All right, I'm not sure if this is going to play for you all, so I'm going to turn my speaker on. Quick change of plans. Here we go. So what happens, is eventually the gravitational waves get so strong, we can actually detect them with lasers that are bouncing around, and we're detecting something very small fractions of an atom size using laser interferometry gravitational wave observatories. And LIGO made the first detection of this early on in 2015, but it's gotten even more interesting, as Anne is going to be talking about. Essentially now we have what I call the gravitational wave electromagnetic sources, which I like to think of as dancing zombie Banshees. They dance around one each other. They're zombies with their neutron stars. They merge and we create the jet. That jet creates a kilonova of material that we can see in optical, and the jet interacts with the interstellar medium, which creates this afterglow, which we can see in a variety of places across the electromagnetic spectrum. Now, I've talked a lot about vampires, werewolves, zombies, banshees, a whole bunch of scary things, but I want to assure you guys there's no need to panic. All these stellar undead are very far away. As a matter of fact, one of the things we've been able to do at AAVSO is tell exactly how far away some of these objects are. So if you remember that object SS Sig, the reason I started getting involved in the AAVSO was because I was interested in SS Sig as it went into one of these outbursts. And first we had AAVSO help out with us to tell us when it was going to outburst. And then we started seeing something very interesting in our radio observations. We started to see evidence that we can measure the change in the position as the Earth orbits around the sun of the object, because it's a little bit far away from us, but not very far away. And so using this parallax technique and using AAVSO members to tell us when to observe, we're able to measure exactly how far away this object is to about 1% precision, solving a long-term issue and finding out that this object is about around 350 or so light years away. So with that, I'd like to thank you all for listening to this. I hope that I haven't gone over, and I will turn it on to the next speaker.
Wonderful. Thank you, Greg. Next, we're going to hear from Arto Oksanen talking about observing GRB optical afterglows. Arto, all yours. There we are. And you can unmute yourself.
Okay.
Let's get started.
Can you hear me now?
Yes, thank you.
Okay. Yeah. I'm Arto Oksanen from Finland. I am an amateur astronomer and AAVSO observer, and I will talk about a bit of gamma ray bursts and observing the afterglows. So, So first, a brief history of GRBs. They were discovered accidentally by Vela satellites launched by USA in 60s to monitor nuclear weapon tests. And I think it was a big surprise that they saw gamma ray bursts coming from outer space instead of ground from nuclear tests. And it was a big mystery and classified information for a long time because nobody knew what was it. But soon, in the 90s, the NASA launched Compton gamma ray observer to observe these gamma rays, and it was able to localize those GRBs within a few degrees on the space. They could tell which direction those gamma rays came from. And also they set up a global alert network called Gamma Ray Coordinates Network. And the main result of this Compton satellite was that they discovered that gamma ray bursts came from all directions. They were not concentrated on Milky Way or anything else. It was quite isotropic in distribution. It showed 2,704 gamma ray bursts in 9 years. So this GCN coordinates network, it's operated by NASA, and it consists of several satellites and space probes, equipment with gamma ray instruments, so they can localize those gamma rays from space, and they right away send the information to the ground station, and then this GCN network distributes those coordinates all over the world. Ground-based telescopes that then can try to observe the same GRB. And the very first optical afterglow was found in 1997 by William Herschel telescope in La Palma, Canary Islands. And it was able to image this fading afterglow of GRB 970228 right after another satellite, Beppo-Sachs, used those Compton coordinates and found a fading X-ray afterglow. So it was able to localize it much better than Compton. So then the William Herschel telescope took this left-hand image of the afterglow, and on the right-hand side it's the same area image 1 week later, and the afterglow had faded away. And this confirmed that these gamma ray bursts are happening in cosmological distances, very, very far away, distant galaxies. Another important gamma ray burst, especially for me, was this GRB 990123. It was observed by a small robotic telescope called ROTSE, and it was observing it kind of real time right after when Compton saw the gamma rays, and it took 2 images per minute and saw very bright optical transient. Magnitude 9 was the brightest point. Here are some 4 pictures taken by ROTSE, and you can see in the second picture taken about 1 minute after the GRB event, the gamma ray event. There you can see the 9 magnitude afterglow. And in 10 minutes, it was almost gone. So everything happened very quickly, but the afterglow was very bright, 9 magnitude. And as Greg already told everybody, this is how the GRB engine is working. It's kind of I would say it's a bird cry of a black hole, not a dead cry of a star. But when the star black hole is burned, then it gives this strong beam of gamma rays and the optical and X-ray and radio afterglow if this jet collides with some material around surrounding this new black hole. Okay, and my personal interest to GRBs started in 1995. I was then working at Canary Islands at the Nordic Optical Telescope and reading a Sky and Telescope magazine in the kitchen. And there was a very interesting article about GRBs, and then nobody knew what they really are. It was really interesting, and I thought it might be great to be able to observe something like that with my own telescope. So, and when the first optical afterglow was discovered in 1996, and especially in 1999 when this magnitude 9 Roche gamma ray afterglow was seen, I wrote to NASA and asked if it's possible for amateur astronomer to join this GCN network and try to catch some bright afterglow like what Roche saw, because I thought it is possible. And I was accepted in, and I then got an email alerts from NASA, and I had access to GCN circulars also to post them if I wanted. And I even implemented a socket interface that was very quick, fast. In few seconds, I got the alerts from NASA. And then I joined to AVSO and AVSO GRB network. That was my main reason to join AVSO, was this gamma ray bursts, and I was quite active in early 2000. So then about my observations. I started observing gamma ray bursts not with my own 10-inch telescope, but using the telescope of my astronomical club. There's a Neutron observatory about 20 kilometers from the center of our town, Jyväskylä. And there are 2 Meade LX200 telescopes and a CCD camera in dark rural site. And less than 1 year, I got my first optical afterglow. It was quite old at that moment, but still detectable, 20 magnitudes. I had to take a 40-minute exposure. That was all I could, because there was a cloud front coming and I couldn't take any more images. And taking a picture of optical afterglow is pretty similar as deep sky imaging. You just take multiple images and stack them together to see find objects like this magnitude 20. And next year, 2001, I and a couple of colleagues from my astronomical club, we were able to observe another GRB. This time we got a light curve, basically taking many pictures during the night and measuring the magnitudes just like with variable stars. It's nothing stranger than observing variable stars, but you need to find the star. It's that's the only difficulty there. And this was observed with actually three filters. We could see it getting fainter in both in red band and V band. This wasn't quite a new burst as either. It was started about 12 hours after the burst, because that's when it got dark in Finland. Another important gamma ray burst was in 2003 on March 29th. It was so-called Monster GRB. The afterglow was found 90 minutes after the gamma ray event at a magnitude 12.5 in Australia, and a few hours later it was observable in Finland. And then I was observing it with the CCD camera, and two friends of mine were observing it visually with their own telescopes. And this is the only gamma ray burst afterglow that has been ever seen visually. Those two Finnish amateur astronomers are the only one who have seen it. Something like that. It was also, this was a close by gamma ray burst. Redshift was only 0.16, so it was 1.5 billion light years away. So pretty close as a gamma ray burst goes. They are usually somewhere about 10 billion light years away. Because it was so close by, this one, it was observable for a long time. And here is the AVSO data of that gamma ray burst. It was observed by 22 observers, and altogether 377 data points. And my data is 78 of those, observed in three nights. It was observable almost a week. It was 6 days later. This is the last data point. And here's a drawing by Markus Tuukkanen, who was the other guy observing it, this afterglow with his 50-centimeter Dobsonian telescope. But there have been some reports by observers who have seen some rapidly brightening and then fading objects with their telescopes. Maybe they have been so-called orphan GRBs that doesn't have had gamma ray burst information. Then 2004, there was the NASA's launched SWIFT telescope. It was a telescope that is catching gamma ray burst on the fly. It has 3 instruments on board. It has a gamma ray telescope that localize gamma rays in within 3 arc minutes on the sky in just a few seconds, and it relays that information to the ground station. Then the telescope, the satellite slews itself and turns its X-ray telescope to these gamma ray coordinates and gets image of this fading X-ray afterglow in 90 seconds. And it has also 30 centimeter optical telescope, and it takes a picture of that, the same coordinates, and if there is afterglow, it will relay that information in 5 minutes to the ground station. So after this SWIFT, it was very difficult to discover afterglows from the ground. But it was not impossible. Nowadays, I'm usually observing with the Hankasalmi observatory. There we have a robotic telescope, 16-inch RC optical Cvqni telescope on Paramount ME mount, and have a CCD camera on it. And it's even darker sight than this Neutron observatory, and it's being fully remotely operable, and it's easy and quick to use every night, anytime when the sky is clear. So for this GRB 07-10-10, October 10th, 2007, and the B, meaning that was the second GRB on that day. There was the SWIFT observed this GRB at 20:45 UT, and 1 minute later I got this text message on my mobile phone, and saw that it was quite bright in gamma rays, and it was located in Ursa Major, quite low on our northern horizon. And that's a kind of a sweet spot for observers in Finland, because it's a very difficult place to observe by anyone else. So if you see the Earth from the direction of this gamma ray burst, you can see that the most of the globe is on daytime, and only Finland and other Nordic countries there are in night. And from here you can observe anything from that direction. So I tried to observe it. Our telescope was already in 10 minutes or so, and I started my script, taking several 1-minute exposures, and 2 minutes after 9 o'clock I had downloaded the first frame and was comparing it with the Digital Sky Survey reference image, and it was quite visible even on the first picture that there was afterglow, an extra star in my image compared to the Digital Sky Survey. But I took several images and saw that it was not moving, so it was not a minor planet or something like that, and it was also fading, so I was quite confident that it was afterglow. And I emailed to AVSO and talked many times with Matthew Templeton then, and Matthew then wrote the GCN report, and it was published 1.5 hours later. So, and it was a second GRB optical afterglow found by an amateur astronomer. And here's the GCN circular telling about the observation written by Matthew. And it was also published in JAVSO volume 36, together with Matthew and Arni Henden and David Kahn from Germany. So why it was not observed by Swift? There was a message from NASA that Swift was in process of returning to normal operations after some, I think, software glitch or something, and the automatic slewing to GRBs was disabled. So it was not doing it automatically at that time. But it observed it after my observations, then one hour later. And the second discovery was 7 years later in 2014. Then I used Casey Harlington's observatory in Animas, New Mexico. There are two 40-centimeter Cassegrain telescopes, remotely operable. And this time I wasn't who took the actual images. I asked my friend who was operating those telescopes if he could take a picture of the coordinates, because I saw on the GCN message that there was a X-ray afterglow, but the optical telescope was not available at that time. I didn't know why, but I thought it might be possible to beat a Swift again. So Petri took those images and sent them to me, and I analyzed them and found an optical afterglow. And here it is on the arrow point. Quite faint, but easily seen. It was the third optical afterglow discovered by an amateur astronomer. And here's the GCN report, just telling the coordinates and magnitude. And why Swift didn't see this one? It was again some technical problem. This time someone was deleting some files on the server and the automatic pipeline didn't work. So Swift took the images with the optical telescope just 54 seconds after the trigger, but processing was delayed. And here are the all three optical afterglows discovered by amateur astronomers. The first one was found by Berto Monard from South Africa, and the second and third was me and my colleagues. And that's a complete list by this time. And here's a quick recipe how to find GRB optical afterglows. You have to be prepared. You can practice and practice and practice, take images of GRB coordinates and learn how and when some bursts have a potential to have an optical afterglow. Having a large telescope and CCD camera helps, of course. And you have to be lucky because you have to have a good observing conditions, nighttime and clear sky. And the location of this gamma ray burst must be visible over your local horizon. And you have to have equipment quickly available. And also the other observers must have some unluck. It is good if Swift has some problems and it doesn't observe it with its own telescope in 5 minutes, because no one can beat that. But even if you get the images, you have to analyze them quickly by blinking with digital sky survey or using some software that finds all the stars in your image and compares to the catalog, and also rapidly reporting those discoveries with by the TCN circulars, because that's the official way to report afterglows. And here you can, maybe you can get help from AAVSO. It at least used to be that way, that AAVSO was writing those TCN reports, but if not anymore, then you can always contact me and I will help. Okay, thank you.
Wonderful, Arto. Thank you so much for a very interesting talk. Let's move on to the last presentation of the day, finding the source of gravitational waves in the first few minutes, the Hotshot Citizen Science Project by Anne Zabludov. Anne, all yours.
Thank you very much. It's an honor to be asked to present to you today. Thanks for coming to our digital festival here. I'm going to now share my screen. Can you see that okay?
Not yet.
Okay, just one moment. What about now?
Awesome, thank you.
Oh, fantastic. Okay, good. All right, and I'd like to just check one thing, please. It does not look like, there we go. So again, I appreciate the opportunity to speak with you today. In particular, I'm looking for the help of non-professional astronomers around the world. We just heard a great introduction about some of the astrophysical beasts that lie out in the sky and that may be there for our taking as astronomers. And we also heard a wonderful talk about some of the, well, the only discoveries of the optical counterparts of gamma ray bursts. And what I'd like to talk about today is to encourage you to think about going after some of the sources of gravitational wave objects that are now being discovered for the first time. These are sources that are often a type of gamma ray burst. They can be short gamma ray bursts, but there's a lot of controversy as to how often these particular sources will have a jet that is narrow and pointed enough so that we receive the gamma ray burst light on Earth. Even when we do, it can be very, very difficult to localize in the sky where that source is coming from. And as I'll describe in a minute, the gravitational wave detectors are not light detectors at all. They're detecting gravitational waves, and their ability to localize where the object is in the sky is really very poor, even though they're extraordinary technical accomplishments. So if you are a non-professional astronomer, a citizen scientist who is interested in hunting for the location in the sky where gravitational waves emanate, it's a bit of a challenge because they literally could be almost anywhere, a true needle in this haystack. And I'd like to describe a little bit later in my talk one methodology by which you could help us, we professional astronomers, actually hone in on these sources. So I want to start by just mentioning, giving a call out to the Hotshots Citizen Science Project. That is this project where we are hoping that professional and non-professional astronomers can get together to very quickly identify where in the sky the gravitational waves are coming from. And what's important about that is there's a lot of physics in those first few minutes after the gravitational wave source is detected. And if it takes a long time to find out where the light from that source is emanating from, then we lose a lot of information that we'd otherwise like to have. So gravitational waves are thought to come from different kinds of binary collisions. Now, this is what you're seeing here is an artist's representation of one kind of astrophysical binary collision, and it's between two neutron stars. Gravitational waves can also come from a neutron star merging with a black hole, or two black holes merging with one another. But we're pretty sure that when two neutron stars merge together, they briefly form a more massive neutron star, followed by a black hole in fractions of a second. And during that time, it's possible for light to escape the system. Whereas if the system starts out as black holes or forms a black hole immediately, light is not going to escape by definition. It's a black hole. Although people are debating some loopholes in those ideas now. But if we focus on neutron star mergers, and Greg already described what neutron stars are to you, gravitational waves are going to arise when you have two accelerating masses and a system that is not spherically or cylindrically symmetric, and they inspiral towards one another and collide. And at that moment, as I said, they end up making a more massive neutron star and then a black hole, but they also, in the process, throw out big gobs of neutrons, which then interact with nuclei that are around and grow those nuclei, change their position on the periodic table by adding neutrons, and those neutrons decay into protons. You change the elements into other elements, and you emit light radiation. And if that light radiation gets emitted and we know where it's emitted from, we can study the system in combination with those gravitational waves. Let me move on to the next slide. So as you see in the right lower corner, that is this extraordinary, piece of this extraordinary LIGO experiment, which basically consists of two perpendicular 4-kilometer length arms in extraordinarily high quality vacuums. These two perpendicular arm systems is located in Washington State, the other in Louisiana. And what they do is actually measure when gravitational waves lap up against the Earth and cause a stretching of the Earth in one direction and a compression in the other. If you can send lasers down these 4-kilometer arms in these very precise vacuums and measure the lengths of those arms extremely precisely, and by that I mean to within 1/10,000th the width of a proton, remarkably, you can see the actual lengthening of one arm relative to another as the waves compress and stretch the Earth and all of us in that moment. So it's a very small signal, but the fact that one arm stretches in one direction while the other compresses in the other direction and vice versa means that it is possible to identify the passage of these gravitational waves when they occur and they're strong enough from a so-called kilonova, one of these mergers of neutron stars. Now, that's what these gravitational waves experiments can do, and they've been remarkably successful at it since about 2015, when they first detected the merger of two black holes. And then in 2017, when they detected the merger of two neutron stars like the artist's conception shown here. But as I mentioned earlier, while they could detect the existence of such an event, they didn't really know very well where it was on the sky. So you can imagine that there might be potentially thousands of galaxies where those two particular neutron stars back in 2017 may have merged together. And LIGO could not by itself tell us where that was and which galaxy that merger of two neutron stars had occurred in. If you take a look at this projection on the sky, upwards is the northern hemisphere of Earth, downwards is the southern hemisphere of Earth. You can see a couple of bananas, they're called, but they're bananas of uncertainty. And those are the regions in the sky whereby Virgo and its companion in Italy, where LIGO and its companion Virgo in Italy managed to localize the emanation of gravitational waves from this event. But unfortunately, that's a pretty big chunk of sky. It can be as large as 150 moon sizes, which is an enormous space, as you well know, to start searching, even if you have a large field of view in your telescope. So what did people do? People knew gravitational waves occurred from somewhere in this banana. They also knew that there were literally thousands of galaxies enclosed in that region of the sky. And where do you look first? How do you seek out this electromagnetic source, this light emission from this collapse of this collision of these two neutron stars? So there were two basic strategies that were employed by the professional astronomer community. One was, as you might well imagine, to look at very large chunks of this picture, larger than moon sizes or a sizable fraction of the moon size, and all the galaxies within those chunks to try to see if something had changed from one night previously to the night of the discovery of the gravitational wave source. But in that case, you don't have great spatial resolution. Your ability to see very, very faint objects in that entire large field is limited. So then other people at the same time hurried up and tried to take a different approach, and that was they attempted to narrow down out of these thousands of galaxies which galaxies might be most likely to host a neutron star binary merger. Now that's quite a guessing game because we don't really understand why neutron star binaries form, if they form, better in some galaxies than others, but you can make some educated guesses about that and try to narrow your list down to hundreds of potential galaxy targets. And so that's what people did, and they started looking at them one at a time with the world's professional telescopes. Well, it took them a while, but they found it. They ultimately found it in this galaxy. This galaxy is NGC 4993. The gravitational wave event was 170817, that was its name. And this galaxy is located about 130 million light years from the Earth. And what you see on the left is actually a Hubble Space Telescope picture of it before, and a Hubble Space Telescope picture of it after the new afterglow from these decaying elements in the surroundings of this neutron star binary collision started emitting light and was ultimately detected on Earth. And you can see this new, it looks like a point source, it's a star of appearance in the picture of the galaxy on the right. So finally, the light from this object was detected, and this ushered in the era of what people call multi-messenger astronomy, where you get information not just from one kind of detector, say the gravitational wave detector LIGO, but also another kind of detector, telescope, measuring, in this case, the optical light or the infrared light from this source, or the ultraviolet light from this source. And the rub here is that it took the professional astronomer community 11.5 hours to find this, because they had these two modalities of searches going, the big chunks of sky with poor spatial resolution, not very sensitive, and the individual galaxy hunt. More or less one at a time or a few at a time, And it's very, very difficult to quickly track down where the source of the gravitational waves were. So we'd like to examine the possibility with you of another approach. And it's a crowdsourcing approach. And in this case, one might imagine taking the thousands of galaxies that were in that banana of uncertainty that I showed you, that LIGO identified, and assigning one galaxy or a few to individual citizen scientist observers. And the idea would be that at the time of the gravitational wave alert, you would receive, if you sign up with us on the Hotshots project, an automated message with a finding chart to go and take a picture of your galaxy. We may work this democratically. If we have enough volunteers, we may ask several people to look at the same galaxy or the same field with a few galaxies in it. But the point is that we will send you a finding chart of the before picture, and we will ask you to compare that to what you're seeing in the image that you take. And we will match, given the information you've previously given to us, to your field of view, to your filter, to make that comparison as easy to make as possible. We will also have a system in place by which, should you choose to do so, your image would be automatically uploaded to a public website. And the idea there would be, if you're observing robotically, say, or you're just very sleepy, or you're not sure, you could have those images perused by anyone, not just those who own telescopes, but people who are interested in doing the identification of these new star-like objects that appear in the galaxy. And so we're in effect crowdsourcing the crowdsourcing. And the ideal would be to find something that has changed in or about the galaxy within the first half an hour of the LIGO alert going out, whereby we sign up not just a few interested citizen astronomers, but hundreds of citizen astronomers, or even potentially thousands of citizen astronomers who have the capability to take these images and who are willing to upload them to a public site so that we have lots of eyeballs on the comparison, the reference image, and the new image to see if we can discover a new point of light. This is our webpage. You can see the address for it in the lower right-hand corner. You can go to it if you're interested, learn a little bit more about the project, and most importantly, sign up. This is how you would do that. You could give us your name, give us your email. You tell us where you are in the world, what the GPS latitude and longitude are of your telescope, because our software has to match the right galaxy to you. It has to match the galaxy that you can observe at the time of the LIGO alert to you. So we need to know where your telescope is. We'd like to know how big your telescope is, its diameter. We'd like to know the field of view. We'd like a little bit of information about the kind of camera that you have. And perhaps most importantly, in that last window at the bottom, we'd like to know how long it would take for you to detect a 19th magnitude star without any kind of filter. We'd also like to know if you typically observe in person or robotically or both, because we're currently working with different manufacturers to engage them to put in voluntary interrupts into their software, whereby even if you are sleeping and things are going robotically, it will interrupt your queue, observe for us, upload the image, and you will get credit, but you don't have to wake up for it. So we have over 100 people around the world. This is not actually a picture of pictures of those people. These are just folks images that I grabbed from different websites just to give you a sense of the abundance of volunteers that we have, not our specific volunteers, but we have over 100 people, citizen astronomers and observatories signed up to be part of this network, this project. Again, to do everything simultaneously as opposed to one at a time, but to focus on individual galaxies and that kind of resolution that that provides. There are over 300,000 galaxies that we have now cataloged that are potentially at the distance that a gravitational wave source could be detected at. And so any of these galaxies could possibly host a neutron-neutron star merger that would produce an afterglow that could be detected by one of you. And so we are working now with computer scientists and mathematicians to come up with some algorithms to best identify galaxies, prioritize galaxies that are most likely to be those that host neutron star mergers, but are also the best assignments to those observers that sign up with us. Here's an example of our alert system. This is one of the things that you would get from us if you signed up from us when we go live in the next few months. We are not currently live for the general community. We're still shaking things down. But this was developed by Chris Michael, who is our project manager. And what you can see in the top part of the top panel is a map of the sky, like I showed you earlier, except you can see the northern hemisphere this time of Earth and the southern hemisphere. And you can also see the bananas of uncertainty from LIGO for this particular gravitational wave detection. And those are these sort of yellow, orange, red contours that you're seeing in that top panel. And what you see in the bottom panel is our algorithm that has immediately matched the information from that LIGO alert, where those bananas actually are on the sky and what galaxies lie within them that are potential targets, with observers who have signed up with us. And you can see the overlap both of the nighttime and also where the bananas are and where the observatories are in the bottom panel. As I mentioned, we would like to crowdsource the crowdsourcing. So we envision having a public website where one can see both the reference image, which, for example, could be the image that you see to the left in each of these dual, these paired images, with the image or a similar image that with the same field of view, similar filter or non-filter taken by the observer on the right. And the idea would be to invite anyone who is interested in working on this to compare the pairs of images and see whether or not they identify visually a change. So for example, I'm sure the quick-eyed among you have already seen to the lower left, the galaxy I showed you earlier that hosted this now famous gravitational wave event, and it's afterglow, and the arrow's there to help, but you can see the optical counterpart that was discovered 11.5 long period after the 11.5 hours after the event occurred. So we'd like to go faster than that, and we'd like your help to do it. So please do check out the website that you can see on the lower right hand. It's my first initial last name.wixsite.com because we don't have a whole lot of money yet for this project, so we're going with the free software /hotshots. If you go to that and you're interested in signing up with us, please do. If you don't have a telescope and you're interested in being a hunter of the source of gravitational waves, please then wait for our announcement of the public website that would look something like this for you to take part. So thank you again for your time and your interest. And I hope you're willing to get involved.
And thank you for a very interesting presentation. We're going to share the link of your of the webpage of the project with our community at the very end. And if I am allowed to share my screen once more, and with that, I would like to thank all our presenters for their talk. Reminding you all who are attending as well, way more than 100 people on the line. So I'm looking forward to a very interesting discussion. I would like to remind you all that the recordings of this and all our webinars will appear on the AVSO YouTube channel. So please subscribe, and we're going to let you know when different webinars are online. And also I would like to remind you to fill the survey we're going to send you and let us know how we can improve this in future workshops. And again, a reminder to become a member of the AVSO, renew your membership. It's only $85 a year to become a full member with a discount for students. And please consider donating to the AVSO to support. With that, I'd like to acknowledge again Voice Astro, which is a partner of the AVSO in supporting this webinar and has been providing research experiences to students, student teams, and schools on how to perform observations, conduct research, and publish the results in scientific journals. So really, really cool project. Please check out their webpage. And with that, I would like to actually move to Q&A for our panelists. I'd like to remind the participants that if your question, if we don't get to your question, we run out of time, please go to the forum of the High Energy Network and pose your question there, and it's going to get to their panelists. And I would like to start with a general question. I think that is for Greg. Do X-ray binaries that are themselves pulsars suck out material from companion stars continuously or intermittently?
This is a little bit complicated, so I'm going to try to tell a story here. So just bear with me. So there are two types of X-ray binaries. There are high mass X-ray binaries, and there are low mass X-ray binaries. And basically here the mass is the mass of the vampire's victim. So if you're eating a high mass star, you're a high mass X-ray binary. If you're eating a low mass star, you're a low mass X-ray binary. And it turns out that high mass stars tend to have very strong winds. So most of the time, the meal is actually not the black hole neutron stars accretion disk collecting information or collecting material directly from the star. It's actually getting it from the wind. For the low mass X-ray binaries, they're so close to the other star that the outer envelope of the star is already in the regime where the black hole or the neutron star's gravitational control will mean that the material falls onto the disk. The action really tends to occur not because of material falling onto the disk, but material falling from the disk onto the black hole neutron star, or in the case of cataclysmic variables, the white dwarf. And so what happens is most of the time you are actually getting fairly constant transfer from your donor onto the accretion disk, but you're getting transfer onto the accretion, onto the compact object from the accretion disk that is irregular. There's an exception. If you're in a high mass X-ray binary system in a very elliptical orbit, you may actually get a lot of accretion because you dump a lot of mass onto the accretion disk when you're closest to the star's wind. But what happens is, so we really need to be thinking about what's going on for the accretion disk material falling onto the compact object. Sorry for the big intro. Now to the question. So the question is about the X-ray binaries that are themselves pulsars. And it turns out that we know of two populations currently of pulsating X-ray binaries. The first is a type of system called an accreting, this is that active feeding frenzy, accreting millisecond X-ray pulsar. So there are pulsations that are on the order of milliseconds, and they're in the X-rays. The second type is a transitional millisecond pulsar. Here you have, again, millisecond pulsations, but they're radio pulsations. They're the more typical pulsars. We don't know if they're the same type of system that we're seeing in two different parts of their evolution or not at this point. The pulsations are coming from different things, but the pulsations are basically talking about how rapidly the neutron star, in this case, is spinning. For the accreting millisecond X-ray pulsars, we've only detected the X-ray pulsations, to my knowledge, when they're undergoing these feeding frenzies, these accretion events, outbursts. For the transitional millisecond pulsars, it's more complicating and more interesting. So these objects actually go from being something that shows the millisecond radio pulsar to acting like an X-ray binary outburst. And so when they're in outbursts, when they're feeding most often is actually when we don't detect the pulsations. But if we go to this, if we go to a part, there's a part when they're feeding very rapidly, and then there's a part when they're feeding about 100th as rapidly as during the feeding frenzy. And there we still see some different behaviors going back and forth. We see one behavior where we're seeing the millisecond pulsations of the radio, and another where we're seeing the X-ray emission get brighter. And we don't know what's going on. We're still trying to figure it out. So it's it is a great question. We don't know exactly what's going on. What we tend to think about is that the radio pulsations tend to come about because of the magnetic field of the neutron star. And accretion, we think, will tend to bury the magnetic field below the surface from where you can see it. And so we think that actually it's when you're accreting that you're not going to be radio pulsating.
Thank you, Greg. There's a question for Arto, actually. How did you make your photometry so detailed for GRBs? Did you use IRAF, PixInsight? What kind of software do you use?
Arto, you're muted.
He's not muted. Here you go.
We still can't hear you, Arto. Have you muted your headphone? Not.
So let me move on to another question while we're solving this technical problem. And this has to do with gravitational waves. There is an individual who said last year participated in an alert with the grandma group, and during the alert we received a list in Excel of several targets, more than 100 available by continent. How do you process? And when somebody is getting 100 targets,
Changing my
We won't do that.
microphone here.
The whole idea of the
Can you hear me now?
is to have enough people to
I
simultaneously
can't hear you.
each look at one or two targets for us. If their field of view is sufficiently large that it encompasses more than a few targets, we would take that into account.
You can hear me, but I can't hear you. Okay. If you can hear me, then I just answer. I've been using many different software packages, and it's just like measuring any variable star. So I have used IRAF sometimes, but not usually. I'm usually using my own photometry script. I've written myself with VB script, and sometimes I'm using MaximDL, just doing some quick and dirty photometry from one frame. So nothing fancy. You don't need any special tools for afterglows.
Awesome. Thank you, Arto. Thank you.
I still can't hear you.
So let's go back to Anne, because I think that this is a hot question for many people who would like to participate in a citizen science project about gravitational waves. And the question pretty much was that in the past, alerts were sent to volunteers in a batch, as in, an Excel spreadsheet, here's 100 galaxies, go observe. Please let us know how your project is going to actually deal with this.
Yes, so the idea would be to take care of that filtering step where we would not dump that amount of unprioritized targets on you. The idea would be that we would have enough observers that we could simultaneously assign different targets to many different people. So you would only get basically a field to image. That field might include one target, it might include several, but it would be one field for your particular setup. You would not have to move around. The idea would be to save that time.
Nice, thank you. Here's an observation, Greg, and I would like your comment. There's an individual who is asking, I was told once that the government denied knowing about some types of energy bursts, so our adversaries would not know that we could detect them, and thus detect nuclear weapon testing, etc. Maybe just an urban myth, but interesting.
All right, so it's the gamma ray burst story is very interesting. As Ardo mentioned, the gamma ray bursts were sort of had to do, we detected them because we launched satellites that were meant to detect nuclear events on Earth. From what I know, I don't think that the original research was classified. I thought it was unclassified, but that doesn't mean that they were necessarily announcing it left and right what they were doing. I do know that they were recording stuff that wasn't actually couldn't clearly be associated with tests on Earth, and they were definitely recording that, and it took several years before people started looking at that data. So I found a little bit of an extra history. I haven't read it in detail. So my guess is it's a mixture of urban legend and the fact that there was some stuff that was delayed, but I also have not read all the individual books that are referenced in this particular web link that I attached, so I may be incorrect.
Thank you, Greg. Anne, a question for you, and actually it has emerged in a couple of different forms in our Q&A, but the gist is the mean gravitational wave afterglow going to be less than magnitude 19? Or I guess the question is how bright can they get so that we know who can actually participate in the project?
And so LIGO sensitivity actually currently restricts detections to within 200 megaparsecs. And it turns out that the expectations for the optical afterglow could then be anywhere between 15th to 19th magnitude. They're not expected to be, by definition, these sources will not be at typical GRB distances. They'll be a lot closer. However, it is thought that these short duration kilonovae gamma ray bursts, if they have a gamma ray component, are a little bit fainter in gamma rays, and people are still arguing about how bright they're likely to be at other wavelengths. They are extraordinary sources. They are very energetic. They are probably release about a 10th to 100th what you'd expect of in a hypernova, supernova event. But they are 1,000 times brighter than a classical nova, and that's why they're called kilonova.
So a follow-up question to that, are there any nearby objects which can create gravitational waves strong enough to cause visual effects on Earth?
Wow, I hadn't thought about that. That's actually really interesting. I would imagine that were there to be, we'd have worse problems worrying about that, because you'd have to scale up to the resolution of your eyes compared to that 1/10,000th of a proton width, and that's going to bring your objects in so much closer to Earth, and the radiation that we were talking about producing these other wavelengths would probably be highly damaging to us. But I hadn't thought about that. That's a really good, interesting calculation to start to do. Thank you.
Well, we'll give you a couple of weeks then to come back with the answer. Here's another question for you. If we take images of random galaxies, what are the chances that rather than finding a GRB, we find a supernova?
Yes, so that's a great question. It's probably about 1%. So that's another reason why it's really important that we have a lot of people involved in this project who are observing the sky simultaneously and quickly after the alert. Some of whom may be observing the same galaxy, but covering hundreds of potential target galaxies at once, because it's very possible that there will be an interloping supernova in one of them.
I will attempt another question to Arto. Arto, can you hear me?
Perhaps we can type it into Ardo
Yes.
for him.
Oh, you can hear me. There you go.
You can hear us.
Awesome, thank you. How does one determine at what time the GRB event occurred when observing the afterglow? So for example, how do observers understand whether it's T plus 1 or T plus 10? How do we know?
You get the GRB time when you get the alert, or you can get it from the TCN website. So that's usually known. It's usually known when the GRB alert happened, and then it's just time from that.
Awesome.
Ardo, can I ask a follow-up question of you?
Hmm?
Can I ask a follow-up question of you?
Yeah.
So,
yes.
well, one of the things that Anne talked about, I thought you also talked about, was the idea that we might be able to detect the afterglows of gamma ray bursts, even if we don't detect the gamma ray burst itself. So,
Yes.
if we just detect an afterglow, is there any way we can get at knowing whether it's T plus 1 or T plus 10, or are we just gonna have to live with a guess? Or
Yeah, I don't know. Usually the maximum brightness is within 1 minute of the GRB. So if you see something brightening and going away, it happened just then, not hours or days before.
thanks.
A question for whomever has the answer, because I really do not know. Could you use a DSLR for observations, and what kind of objects of this type you could observe with the DSLR camera?
So,
I guess you could not go as faint as 19, of course, but what type of objects could you observe?
So I guess I'm going to take a stab at this, and I apologize. There are people that are on the other end that are actually observers that use this a lot more than I do. But you have to think about, for the DSLR, not just the camera, but the actual lens itself. And so very few people, I think, have DSLR lenses that are bigger than about, I don't know, what is that, 4 inches, 6 inch, diameter lenses. Maybe some people do, but so you're limited to sort of the sub 8-inch class of telescopes. And so I suspect that you would only be able to detect such an object if it was a local group gamma ray burst or supernova. Because otherwise, I think people with the meter class telescopes might be able to get at the sort of 19th magnitude. And if you go from 1 meter diameter down to 8 inches is what? 20 centimeters, 0.2. That's a factor of 25 times factor of 25 times fainter, which is going to be a factor of about 8 magnitudes fainter. So you're down to sort of 11th magnitude, 12th magnitude, if I did that in my head correctly. And it's possible I didn't do it in my head correctly. So I think you may be only hoping for that galactic supernova or gamma ray burst. The good news is we are overdue for one, and we're crossing our fingers it happens at a time when tons of people can observe it.
So this follow-up question, what is the closest GRB to the Earth? And actually, I'd like to say, which is the closest GRB candidate to the Earth? Do we have a candidate right now? Do we know?
No, you can't know them before it happens. So
Yeah.
just a dying star. It's
Yeah.
they are hundreds of millions of light years away usually, and even then they are quite close.
Yeah.
So there are gamma ray bursts that have been associated with supernovas. I forget which supernova it actually is, the type, or Ardo may remember this more. And I don't recall any of those being in our immediate galactic neighbors, but I wouldn't be surprised if we've had that type of supernova within about 30 million light years of Earth, if not 3 million light years of Earth.
Oh, quite safe, right? You dare say.
We're very safe. There's a wonderful book. If you're worried about astronomical disasters, Phil Platt has a wonderful book about them, and you can find out about specifically about gamma ray bursts and what's the possibilities of that. I forget the name of the book. I will look for it and post it on the chat.
Okay, that sounds cool.
Yeah.
Now, go ahead.
There is a gamma ray burst 080319b that was so-called naked eye GRB. It was a 6th magnitude on the peak, and I think it was also the closest to the Earth. I don't know. Yeah, maybe. Redshift 0.9, 7.5 billion. It was very bright, but it was not the closest. But something like that you can easily image with DSLR camera with even standard lens, and if you put it behind a telescope, you can reach almost the same than with the CCD camera.
Cool. That's an excellent advice and a really good point. And actually, Arto, there are a couple of questions relevant to how do you sign up for GRB alerts? Where would you actually advise people to sign up if they want to do follow-ups of GRBs?
I don't know. It used to be a service by AAVSO. I don't know if it exists anymore. So AAVSO was subscribing TCN alerts and then distributing to the observers. That's the easy way. I don't think NASA will accept a bunch of amateurs anymore to directly to the TCN mailing list, because it's already thousands of subscribers, I think so.
So this is something that our high energy network could actually look into and see whether we can do something about providing appropriate GRB alerts to the community that is interested in. So
but if there was just a couple of observers, I can redistribute my emails. Just contact me.
Where do you get your alerts from? What's the source
Directly from NASA.
Directly, okay.
Yeah, I joined then year 2000, 1999 into the THN. It was then possible.
All right, thank you. Now, for hotshots, on the question about how long an exposure is needed for 19th magnitude, what signal to noise ratio is needed?
The answer is, can you see it relative to the reference image? So we're not planning to do actual science with the image. We just want your view on whether or not it is possible to see the source compared to the reference image.
So would you say that's like a signal to noise of about ratio of about 5 then, Anne?
Yeah, I would say it's probably around 5.
So now you see it, now you don't.
We don't need you to burn it in. We'd rather know quickly rather than well. And then we'll also take a look. We'll be following up with other telescopes at that point. And I neglected to mention, I alluded to it, but I neglected to mention that should you be the person to take the image and or the person who makes the discovery from the public website from the image, you will get credit in the scientific literature. You will be our collaborator on the project, for sure. Anything that gets written up, you'll be on.
It's really important to point out that all those projects that we're encouraging our community to participate in are collaborative efforts. So co-authorship and acknowledgement is something that we're going to go for. Yeah, absolutely. Thank you, Anne, actually. So here's another, let's go for a general question. What is the expected range of magnitude of neutron star mergers? Is there one?
So are you talking about whether it's observable optically?
I will go with that assumption, yes.
Okay, yes, no, I mean, I think again, for neutron star mergers within LIGO's sensitivity limit, so out to the distances to which LIGO expects to detect gravitational waves, the expectation is that if you can get down to 19th magnitude, it can be extraordinarily helpful to the project. And it may be brighter.
Okay, cool. Now, is there anything optical or electromagnetic counterparts for black hole mergers? Ta-da!
Well, certainly initial models suggested no, and it's certainly true that there have been black hole mergers detected by gravitational wave interferometers, and there has been no counterpart detected. Now, of course, the absence of evidence is not necessarily evidence of absence, but theoretically, it's much harder to get light to escape from a system where you have a black hole involved. But black hole neutron star mergers, it's thought there may be a possibility of electromagnetic radiation. But we'd like to focus, at least initially, this project on neutron star mergers, where we know there should be an optical counterpart, and we just have to find it.
Dan, can I follow up that question to you?
Of course.
So you mentioned the black hole neutron star versus the neutron star mergers. How would, if you were to be considering the black hole neutron star mergers, how would that potentially affect hotshots? Does that mean that you'd have to go further out in volume and therefore to fainter magnitudes, or?
Yes, I mean it's not known right now because we don't have any calibration of what those optical counterparts actually look like empirically. So I think it's certainly an interesting field to go hunting. I guess I'm a little bit leery initially of sending people off in that direction because I want people to feel that there is a strong potential payoff, at least during the early phases of the project, and that we could then expand our repertoire if things are working swimmingly well later.
Awesome. Actually, we have a comment in the chat. So for those who are interested about GRB alerts, it seems that you can get Swift GRB alerts that are distributed, and it actually showcases where Swift is pointing, so you can pre-position your telescope in case there is a burst. For those who just want to have a schedule throughout the night, can actually follow Swift across the sky. There's still no guarantee that you're gonna get one, but hey, I guess that right now it's more of the hunting process of trying to find something that is super exciting, but really sort of risky when it comes to try to identify it. And this is actually really cool science. Here's another question. A supernova typically has an absolute magnitude at 10 parsecs of about 19.4. How much can a kilonova have? Equal or more?
Yeah, so it depends on where the supernova is compared to where the kilonova is in distance. So the kilonova itself is not expected to emit quite as much light as a typical supernova will. You know, a typical supernova is probably 10 or 100 times brighter. A hypernova might be 1,000 times brighter than a kilonova is expected to be in the optical afterglow, but it's more an issue of the distance as well. And so if we're talking about the typical magnitudes that supernovae are found at, that also accounts for supernovae that are discovered at very, very large distances relative to the limits of the LIGO detections and where we expect these gravitational wave counterparts to be.
How frequently do you expect one of those LIGO detections?
Yeah, so I'm not sure we know the answer to that yet because LIGO, you know, they're constantly upgrading both the sensitivity of the detector and its coordination with other facilities, but also their alert software and their degree of false positives and how they decide to put out a public alert based on the information that they're receiving from the instrument. So that was a long-winded answer to the question of I don't really know at this point because we haven't had that much of a time baseline to determine. Based on the discoveries so far of the one system that clearly had this optical counterpart, it's very possible that we'd see at least one per year, but maybe multiple times a year.
Mm-hmm. So how would you recommend that those who are interested in this project from our community be best prepared? How do we prepare for hot shots?
Yes, well, I would recommend going to our website and signing up with us. Not a whole lot is going to happen immediately because we're currently developing the infrastructure for this project. So we will take your information, we will store it in our database, and we'll be extraordinarily appreciative of your interest. And once we actually get our system going, then we will get back in contact with you and say, look, LIGO is operating. We're going to start receiving alerts from LIGO. It's going to be filtered through our system. We're going to then start making assignments to you, and you will be hearing from us when a potentially interesting target occurs.
Wonderful.
And can I follow up?
Sure.
I didn't mean to interrupt. I apologize. So what we would have to wait for hotshots. We have to wait for LIGO, the next run of the LIGO observing run. So first off, the first question would be, when is the next run of LIGO observing? And the other questions related to this is, do you guys have plans to either test out the system ahead of time by perhaps tricking on some supernova or something else to test out the system? And similarly, do you guys also have plans to do the type of things that the LIGO people do, where you actually inject fake data that people don't know about? So for those of you who don't know what the particle physicists do occasionally to test their systems from end to end, they'll actually put a false signal in, and they'll go through the entire process. I hope they stop them before they write too much of the paper, to test everything so that they know where there's a mistake and where there's not mistakes, so that they can be ready when these more rare events occur.
So we certainly do plan some dry runs once our infrastructure is set, and everyone will know that they are in fact dry runs. I'm not intending to put fake data in or to fool people into thinking that and get them excited over a test. But I will definitely tell people that we're doing a test. We could either do it from alerts LIGO puts out as its own test, or we could just do it for Supernovae or something like that. Just to make sure all the bells and whistles work. As far as the fake data notion, I mean, that's more an issue of whether or not you are testing your sensitivity to a detection for real detection. I think our process will be, we want to know if there could be a detection from our non-professional colleagues, and then we want to follow that up with perhaps directly sending that information into the form of an ATEL, and have the community follow it up with telescopes large and small to get as much information as possible quickly. And if it turns out that after we do that, we're in an era of many, many false positives, then obviously we'll have to streamline our process. But we hope to build in enough checks, both visual and otherwise, so that we're not releasing bad information.
Wonderful. And with that, we are at the top of the hour, and I want to be respectful to your time and our participants and our presenters. So I would like to thank you all again, Greg Cvqni, Alex Zabludov, and Arto Oksanen for joining us, for giving very interesting presentations and an overview of the high energy, really, really hot universe in optical wavelengths. We're going to continue this conversation. I'm pretty sure we haven't heard the end of hot shots, if not anything else. This is the beginning. This is the beginning of, I hope, a really fruitful collaboration. I would like to thank everyone who's joined us from all over the world. It's really encouraging and wonderful to see our community coming together under science. I wish you all a wonderful rest of your weekend. Join us again next weekend. We're going to be talking about pulsating stars. Everyone, please stay safe. Thank you so much.
And thank you, Stella and Bert, for all your work behind the scenes.
Thank you. Thank you.
Thank you.
Bye, you guys.
Thank you.
Bye.
Bye. Bye.